but this is based upon the colligative property, boiling point depression. So when you put a solute in your pure solvent, it will change its boiling point. It will decrease the boiling point. Excuse me, freezing point. Freezing point depression. So the colligative property is based upon this change in temperature is equal to the freezing point depression constant for the solvent. In this case, the solvent is lauric acid. It's a fatty acid, lauric acid. Times the molality of the benzoic acid in the lauric acid. And since they don't break up into individual ions, then the I value is 1. So we don't even have to put the I value in here. Yeah. Okay. So what is the K freezing point constant for? Let's put it over here. K freezing point for lauric acid. It's in your method, but I'll write it up here too. Is 3.90. 3.90 degrees C per molal. Or you might write it this way, 3.90 degrees C. Molal is moles per kilogram, right? Moles per kilogram. So in the denominator, if we flip that up, then the kilogram comes up here and the mole goes down here. And this is kilograms of solvent, and this is moles of solute. Okay? All right. So we're after the molecular weight of benzoic acid. So what do we need to know to determine the molecular weight of benzoic acid? 2 factors. We need to know the mass and the number of moles that mass represents. Okay, so when we go through this procedure, you're going to weigh out a certain amount of benzoic acid and dissolve it in the lauric acid. And notice the change in temperature for the freezing point. So you want the change in temperature. That's this one right here. And actually, the absolute value of the change is what we're after. Just drop the negative if there's one. Okay, so we know the mass because we weighed the sample. Now we need to figure the moles. And we get the moles from this expression right here. We know the change in temperature. We know the K value. We can calculate the molality. From that information, we can calculate the molality of the solution that we create with benzoic acid in the lauric acid. So now that we know the molality, that's moles per kilogram. Molality equals moles of benzoic acid per kilogram of lauric acid. We know this one. We know the kilograms of lauric acid too because we weighed it out. Okay. Well, we know the grams, so you have to convert it to kilograms. And then you can solve for this one. Once you solve for that value, it goes in here along with the mass. You can calculate your molecular weight. Okay, let's see. Pre-lab questions. We have discussion. I'm not sure. Let me look at your. This is the key, so I'm not sure what. Let me get a copy of the. Here we go. This is what you're seeing, so I want to do. Oh, there is one pre-lab question. Okay, so we'll do that one. And then there are laboratory questions that you need to answer. So we'll do the pre-lab question. I think the pre-lab question is one that takes you through the procedure so that you get a feel for it. Pre-lab question. All right, a student found that 7.98 grams of lauric acid, so we have mass of lauric acid, is equal to 7.98 grams. Froze at 43.75 degrees Celsius. That's pure lauric acid. So the freezing point, the temperature freezing point of lauric acid is equal to 43.75 degrees C. That's pure lauric acid. The mass of benzoic acid equals 1.03 grams. When you put that grams into that lauric acid, then the freezing point changes. The temperature of the freezing point of the solution now is 39.43 degrees C. Calculate the molar mass of the solute, which is benzoic acid. Okay? All right. So we've got our expression here for molarity, and we know this is mass. I can get confused with molality. So the mass is 1.03 grams. Okay, so we got that. Now what we need is, what's the temperature difference? Right. What's the temperature difference between the pure lauric acid and the solution? So we got 43.75 m subtract 39.43. So the change in temperature is 4.32 degrees C. Okay, and that's equal to the K factor, which is here, 3.9 degrees C per molal times molality. Okay, so we just solve for molality, correct? Divide this one by that one, and you find out the molality of the solution. So I get molality equals 1.1077 moles of lauric acid per kilogram of, moles of benzoic acid per kilogram of lauric acid. There we go. That's the molality. Now, how do we find the moles of benzoic acid? Well, look what happens when you have this many grams of lauric acid. We want to cancel kilograms. So this has to be 7.98 times 10 to the minus 3 kilograms. Correct? Because there are 1,000 grams in a kilogram. So it's 10 to the minus 3. Okay? Or do we need to work that one out?
No.
Oh, okay.
Yeah, you're fine.
Okay, so this one, this molality times 7.98 times 10 to the minus 3 kilograms of lauric acid, this will cancel here and leave us with moles of benzoic acid. So I just need 7.98 exponent 3, change the sign, times. This is 8.84 times 10 to the minus 3 moles of benzoic acid. So that goes right here. 8.84 times 10 to the minus 3 moles. So we divide 1.3 by that, 1.03, and I get 117, rounded to 3 places, grams per mole. That's our experimental value. Okay, it doesn't tell you to do percent error. It just asks you for the value. If we were to do percent error, we would say, was it 122? 122 minus 117 over 122 times 100. Right. So if I do that, 122 enter 117 minus, and then 122 divide times 4.1% error. Okay. Actually, it should be the other way around. 117 minus 122, that would give us a negative value. That tells us that our value is less than the accepted value. So I did them backwards. Or you can just take the absolute value and say, that's the percent error. Some prefer it that way. Okay, that's what we're going to do. The experimental part is figuring out these two values, where you're going to get that value, you're going to get that value from the balance, and then you're going to measure temperature and find the freezing point. First the pure lauric acid and then the solution. So you get these two values. That's what's coming out of this experiment today. And that will allow us to calculate the molar mass of benzoic acid. Okay. All right. I think we got time. So let me make some room up here. That's good. Sometimes you see in a liquid that's freezing.
Oh yeah, I see it now. It's moving.
It's
Yeah, that's kind of cool.
this temperature change here. It went 38 and then up to 38.2. Sometimes what you'll see is what's called the latent heat of fusion. So when you go from a liquid down to a solid, the molecules are slowing down and they're giving up heat. So as they slow down and arrange themselves into that lattice, they give up a little heat and the temperature jumps up. I've never seen it with this experiment before. It's more pronounced if you do it with water. It's very pronounced with water. You'll have a change of 5 degrees.
Yeah. It's about frozen now. Well, it's something like that.
Okay, so let's fill this in. That's all the data. I think our procedure tells you to graph the data.
Yes.
That's why we did that graphing data first. Wouldn't all be great.
Yeah.
Oh.
Would I clean his phone off or anything?
Um. Very least. Should be. See, the lauric acid, benzodic acid is not water soluble, so. Of course, the stream should not come on. It's almost there. So, you think you got the calculations down?
Yes.
Okay.
Yeah. After looking at that, yeah.
I'll post a video on. Price fix. Type it in. School down. So. That's it. For today.
Yeah, I like that ending of the acid part.
What?
That acid part wherever like, it froze, like the freezing point.
Oh, the temperature went up.
Yes, the temperature. Yeah.
That's interesting.
Yeah.
It's not what you'd expect. Called the latent heat of fusion. Let's see. Got a few minutes before my next class comes in.
Yeah, I got the calculations down. I'll look at that again and I'll have it good.
Okay. Back. Where we got it. We do.